Hi, everybody. So in this section, we're doing 11.4, which is the binomial distribution. So let me bring that up for you. So there's only 2 vocabulary words here, and we're actually about to go over them. So you don't necessarily have to worry about them, but if it is confusing to you, the binomial experiments, the binomial distribution we're going through, it'd be great for you to just make sure if you're not quite grasping. And at this point in your education, you should understand if you're fully understanding or you're kind of understanding. And it's important to fully understand in order to make sure you know how to use the concepts, not just define them. So in a binomial experiment, basically what we're doing is you have trials. And it's a probability experiment. You're experimenting to see what the probability is, basically. And there's a fixed number of independent trials, and the probability of successes, P, is the same in every trial. And then failure, Q, right here, is basically whatever is not a success is a failure. So each trial that you're dealing with, there is no maybe, there's no gray area. It's either success or failure, one or the other. Hence the term binomial. There's one or the other option, and that's what we're dealing with here. We're starting with the basics kind of experiment. And then your random variable X is the number of successes in the trial. Okay, it's how many trials, and then your the successes P is the same in every trial. Okay, so let's say we want to know how to do it. Here's how we do it. Step 1, you're going to describe what the trial is going to be. Again, it has to be a trial of success or failure. It worked, it didn't work, nothing in the middle. Then you decide the number of trials that you're going to do. You're going to define what success means, because in order for us to define what P is, I mean, to keep track of P, the successes, we need to know what a success is. Okay, like it gets heads every time, and it's not heads or tails, it's getting heads is the binomial, or getting tails. So it's not, you can't define it as this or this. It's you're reaching 2 coins and they both have tails. That's your success, right? It's not this or this or this type of thing. So then you find theoretical probability of success and failure. So what is a probability? Well, in each one, if you get 2 tails for each coin, that's 0.5 times 0.5, which is 0.25% of success, 1/4 of a chance, because your probability is either tails, tails, heads, tails, tail heads, or heads, heads. And so that's 1/4 of probability of success. Then you describe the random variable X. So you're going to, your random variable is basically 2 tails. And then design and conduct to find the experimental probability. You're going to actually flip coins, 2 coins. Are you going to do it at the same time? Is it going to be one or the other? Those are the details that you need to do when you're designing the experiment. So here's an example. Determine either each experiment is a binomial experiment or can be reduced to binomial experiment. If so, describe a trial, determine the random variable, and state N, P, and Q. All right, that's a lot of explanation, but we can do this. So first of all, let's see if the following can be a binomial experiment. Can it be a success or failure? In a class that consists of 12 male and 13 female, a group of 5 students randomly chosen to see how many males are selected. Okay, so basically, there's not an independent event, right? You have 5 students that's randomly and can either be male or female. 12 male, 13 female. It's not independent. So the probability of choosing a male student changes after each selection. So you could do the successes. So let's say, okay, but you're saying, Ms. P, we could just write it as, well, 5 students is randomly chosen to see how many males are selected. So each one is it male, yes or no? That's correct. But please pay attention to this other part, because it's not always going to hand it to you, because you are now in that upperclassman phase. It's not going to be handed to you, so you have to pay close attention. It not only says that it could have, each trial needs to be a success or failure, but it also says that the probability of success P in the trial is the same. So that means it's the same every time. But when we're dealing with kids here, when we're dealing with this situation, I have 12 male and 13 female. So once I do choose a male, or once I do choose a female, then the probability for the next trial changes. So therefore, because the probability for the next trial changes, it doesn't follow suit with the binomial experiment, right? It needs to be the same. That when you do heads or tails, on a coin, every time you flip a coin, the probability of success is still 50% no matter what. But in this case, because there's a allotted amount of male and female, it changes that. So therefore, this cannot be a binomial experiment. Right? Because the percentage of the probability of the males change every time you go down the line. So let's see the next one, because there's no point in us finding the other things if it can't be a binomial experience. So let's try the next one. A school study found that 65% of students have seen an episode of a specific show. 7 students are randomly asked if they have seen an episode of the show. So you have it can be a thing, because it can be a binomial experiment because they either watch the show, yes, no, oh, not now, no, and it's a 65% rate, 65% of the students. So the probability of the students is 65%. So that's our trial. They're going to ask the students. So our trial right here, if so, describe a trial. So the trial is, we're going to watch show. 7 students are going to be asked, have they watched the show? Yes or no. Okay, that's our description. I don't need complete sentences here, but you might want to write that in a way that makes more sense, but I'm hoping that you understand at this point. So I'm trying not to make these videos too terribly long. And then what it's asking for us is P, Q, and P and Q. So let's go back here and figure out what they're talking about. So we have N is the number of independent trials, right? Our P is successes, and our Q's is our failure. And that's basically, we're taking the success. So the number of trials, our N, is 7. Right? We're going to ask 7 students, that's the number of trials. Our P's number of successes, that would be this, 65, but we always put probability no matter what. And you've learned this when you worked on exponential functions, when we're dealing with exponential growth and decay, that the probability is always in decimals. So I'm going to take this divided by 100, which is 0.65. And our Q is our failure, so it's 1 minus 0.65, so it would be 0.35, right? And those are our 3 variables. So go ahead and write that down. Hopefully that made some sense. And then we're dealing with binomial distribution. So in this case, we're doing the same experiment multiple times and finding the success. We're doing the entire trial and seeing if that's successful. And then we're asking the question, wait a minute, what happens if we do the entire trial again? Okay, and finding the success rate and how close that is every time. Because if you experiment and it's close to the probability, and you experiment again and it's not close to the probability, and we're not talking about individual trials, we're talking about the whole experiment, okay? So we're figuring out that the X successes in N independent trials, and here's the equation for the binomial probability formula. How we find the binomial probability, this is how we find the equation, and on the bottom is what is in the binomial, the mean of the binomial distribution, to figure out the average of all of the trials together. What would be the probability, the mean would be found with this, and then it would be n times p, where n is the number of trials and p is the times the probability of success, right? Because we're trying to find the average. So you're going to find the probability of success for all of them, and you're going to times it by the number of trials you conducted, and that finds the mean of your binomial distribution. So here in this case, if you're not quite sure, well, why do I need this, and when do I need this, and all that sort of stuff will come into light. What we're going to work on is how to actually find these values, and then once you find the values, then we're able to translate it. So let's just focus on finding the values, right? So in this case, number 2, it says a candy company produces strawberry and vanilla flavored candies, 65% of which are strawberry on average. The production line mixes the candies randomly and packages 15 per bag. What is the probability that 7 candies in a bag are strawberry? Okay, so what we need to do is we need to find this probability. So I'm going to go ahead and copy and paste this. So we have this, and we have to start with the obvious, which is finding our variables, just like any other problem. But first, let's figure out what they're asking. They're asking what is the probability that 7 candies in a bag are strawberry. All right, so that means we're looking for 7. 7 will be our variable x, okay? And then we also need to find n, we need to find p, and we need to find q. So let's find those. Our n is 15, right? That's how many trials they did it in. Our p is 0.65, because I'm going to take this and I'll do 0.65, which means our q is our number of failures, which is 0.35. So let's put it in. So the probability of 7, which I don't actually need to do anything here, this is just to tell me what value I'm looking for, is n15c of x, which is 7. Then we have times, again, I'm just going to separate this, 0.65 of x, which is 7, and then times q of n, so 15 minus x. Got everything. Now, this is a combination probability, right? If you haven't dealt with it before, you can go ahead and look at it. Your calculator should be able to show this real quick. So let me pull up Desmus real quick. Okay, so I'm going to show you, and it's again the same step, but I want you to go ahead and hold on. I'm going to open this. Okay, so we're going to go ahead and go to our Google, and we're looking, C stands for combination, so it's combination Desmus. So here it is, combination Desmus. And you can see yours is on there. And our one says n is 15 and combination 7. Oop. 15 combination 7. Perfect. So here is there is 6,435 possibilities, 6,700. Okay, so let me go back to our thing. So now what we're going to do is we're going to find the others. I'm going to broadcast the calculator so we can find the other ones. So just so you're caught up, we found a 15 combination of 7, which is 6,400. Now we need to find this and the other one. So this is 0.65 to the power of 7. So I'm going to bring a calculator. So 0.65 to the power, where is my power? Oh my, power of 7. And so I'm gonna go ahead and copy. Well, no, I'm not gonna copy. Okay, it's 0.0490. I'm gonna try to keep it 4 decimals. 0.0490. I believe that's right? Let me see here. Let's see if I can put this here. Haha, fancy. Okay, so let's just go ahead, bring it down here. Okay, so in this case right here, we're going to do the same thing, except we're going to do q to the power of 15 minus 7. So that's, okay. I was using my fingers. No shame, no shame. Okay, so we're going to do, oh, q. I didn't fill in q. Q would be 0.35, right? So that would be 0.35 to the power of 8. So 0.35 to the power of 8 would be 0.00022251. I know I said stick to 4, but it would just be 0.002. So that would be rough. So I'm going to go ahead and take this, and I'm going to multiply that answer. That takes the whole decimal. So yours might end up different if you're only doing this many or only doing 4, but it does make a difference. So we go there times 0.0490 times 6435. So we have 0.071. My bad. 0.0710, and I times that by 100 to give me my percentage, and it's 7.1%, right? What does that number mean? It just basically is, if I conducted this with 7 candies in a bag, right, it would be 7.1% that they would get strawberry. I'm using the other trials. So that's what this equation gives us, right? The binomial probability formula.